but I'm a physics PhD student studying particle physics, outreach, and education, and I'm going to invite you on an adventure to become particle detectives. We're going to look at the smallest things we can't see with the naked eye, journeying first from bigger things like the air around us and getting smaller and smaller, looking at electrons, the nucleus of atoms, and then I'll invite you at the end to participate and become a model particle detector. Are you ready? Perfect. So for the first part, we're going to try and visualize the air around us. But can anyone see the air in the room? Probably not, and that's a good thing. We normally can't see air, so it's going to be difficult to try and see what air is doing. So I have volunteers who should be able to give out bubble stuff to the people down the middle row. So near the middle, just down like the middle aisle, up this side and this side. And as those are being given out, I'm going to pull out this box, which this is just a regular cardboard box, fancy Kazakhstani cardboard box, with a piece of cardboard and a bag at the end. And when I hit it, I should be able to make vortices of air, and you should be able to feel the air going around the room, but we can't see it because we can't see air. So that's how we're going to use the bubbles to help visualize what's going on. If you're one of the lucky people who got bubbles, please open it up, take the bubble wand out, and blow bubbles up into the air so we can see the bubbles. And we'll just take a minute to let people open it up so we can start filling the room with bubbles. And we want to get as many bubbles as we can. So if you have a bubble thing, just take it out and start making bubbles. And already, we can see beautiful bubbles filling the room. This is a great plug for my friend Paul Landman's show this afternoon at 3. You'll see more bubbles with him going on later. Okay, now we're getting more bubbles. Keep it up, keep it up. Make as many bubbles as you can. And those bubbles, taking up space in the air, will allow us to visualize this vortex going through. So we should be able to start seeing evidence of where the air is being disturbed by this vortex. And so we can see, with the help of the bubbles, which are our first detector, we can see the movement of the air. So we're starting to be able to visualize something that's not previously visible. Okay, and that's probably enough bubbles. If you were blowing the bubbles now, put them away, and we're done with bubbles for now. So we saw that we can see big scale of movement of air. Now, air is made up of different molecules which are moving around, both when I move a vortex through the air or just moving around in random directions. We can help visualize that as well if I take this bottle, which is full of air. We can hear that it's full of air. That gets picked up horribly by the mic. Okay, so we can hear the air in the bottle, but we can't see it, and we can't see it moving faster when we heat it up or slower when we cool it down. For that, I'm going to use a trick. I'm going to use a stopper to keep the air in the bottle, but also a straw, which I'll fill with colored water so we can see the air heating up and cooling down. For this part, can I get 2 volunteers to come help me on stage? You there? Yes, please come up. Oh, and over there, yeah, please come on stage. Welcome. What are your names? Danier. Agata. Nice to meet you. Are you feeling nice and warm today? Okay, warm enough. So I'm going to ask you to make some heat for me. So what I'm going to ask you to do is start rubbing your hands together. And as I prepare this thermometer, I'm going to get my volunteers to get as hot as possible. And to make this thermometer, I'm just going to take a balloon and some colored water, because we can't see the air, but we can see water and we can see colored water. Are you feeling hot yet?
Yes.
Perfect.
Yes. Yes.
So the thermometer's almost ready. Okay, and we'll move it nice and close to the camera so it can pick it up for anyone who's not in the front row and can't see. So once your hands are nice and warm, and notice the level of the thermometer is there, right? Once your hands are nice and hot, then just put them on the thermometer, and we're going to heat it up and see how hot we can get it. So put your hands on, and we see it's starting to go up. We've got some very hot-handed volunteers here. Way to go, guys. And we can see as it's going up that the air inside the bottle is expanded because hotter air will be moving faster. It'll increase the pressure, and that'll cause it to increase volume, so it's pushing the level up the thermometer. So we see this homemade thermometer in action. Just going to get my hands on here to get it. Oh yeah, rub your hands to make it even hotter. Amazing. Let's give a round of applause for my hot-handed volunteers. And thank you, guys. You're hot enough now. You can sit back down. Thank you. Okay, so we've seen with these first two techniques, we can see the air around us, and we can see what it's doing. And air is made of molecules, which are small, but if we're trying to look at the particles that make up the universe, molecules are actually kind of big. They contain multiple atoms. So we're going to look at even smaller things we can't see. So the next thing I want to look at is electrons. And those of you who know about atoms, you'll know that electrons are the outermost part of most atoms. So we're going to try and visualize what some electrons are doing. For this, I'm going to need to set up so I can have a little bit of fire. Who here likes fire? No? Only one person likes fire? Maybe we won't do this part. Who here likes fire? Okay, that's a little bit better. So, in this waste paper bin, I have a number of white powders. And you can see, and I'll hold them close to the camera, you can see these white powders, they look pretty similar to each other. So from the outside, we can't tell the difference between them. There's not much visual difference between them. But they're made of different elements, different kinds of atoms that have different properties of their electrons. Their electrons will have different amounts of energy. And if I light them on fire, then that'll give rise to different colors, because each color of light has a different distinct energy. So for this to be more visual, I'm going to ask if we can turn off the lights for this next part. So can we turn off the lights? Perfect. Okay, now I'm in the dark, and I should have thought of that to look what I was doing while there was light, but I've got some light here. Okay, so I can see what I'm doing, and I'm going to take some potassium chloride, which is one of my unlabeled white powders. And actually, no one can see anything I'm doing, right? Can we get a small amount of light so people can still see me a little bit? If that's too much to ask, I'll do it in complete dark. There we go. That's perfect, just like this. Okay, so it's dark enough people will be able to see the flame, but you'll be able to see that I put some of my white powder that looks just like the other white powders here. And I'm just going to put a little bit of methanol, which will be a fuel which I can burn. Okay, so now I have a beautiful flame here, but you probably can't see it that well, right? It's only about this big, so I'm just going to start spinning this wire waste paper bin, and we should get the flame. Now, shout out, what color does this flame look? What color is this fire? Ah, blue fire. So blue is something we can detect from the potassium, and the potassium gives this characteristic blue color flame. So you have this nice, beautiful blue flame due to the potassium burning. So that's potassium for you. After the potassium, I'm going to move on to another white powder that looks just like all the other white powders. But this one is boric acid, so it's got boron in it, which will give yet a different color. So a little bit of boric acid. And again with my fuel here. And when you can see the flame, when you see a colored flame, shout out what color this flame is. Ah, green. So I have a green fire tornado. And green is typical of boron. So that's the color we get from boric acid. That's what we're detecting again from this white powder that looks the same as all the white powders, but with the magic of fire, we can tell what the powder is. Beautiful green fire. So that was our boron. Next, I'm going to go to a more usual substance. I'm going to use sodium chloride. I'm guessing a number of you have eaten this today. Does anyone know the common name for sodium chloride? If you do, shout it out. Salt. So it's just table salt. And I know I personally had some salt with breakfast. Let's see what color we get when we have sodium chloride or table salt. So what color flame are we getting now? Ah, an orange flame. So we're getting this typical sodium orange color. And I'm hearing some people say blue and red, so there's a couple other colors we're getting in there. I'm not quite sure why. There might be something dirty messing it up, but the orange color is the typical sodium color that I was hoping to get. And we kind of have a mix of other things polluting that. But you guys saw the orange, right? Yes? Okay. Medium confident confirmation. Okay, so we do have orange, so we're able to see that sodium's present in that white powder as well. So with this method, we're able to detect things that we couldn't see with the naked eye that tells us a little bit about the behavior of the electrons there. So now that we've seen the electrons, and just waiting till the fire goes out, never leave a flame unattended. Okay, now that we've seen a little bit about what the electrons are doing on the outside of the atom, then I'm going to ask if we can turn the lights on, and we're going to look at the next steps smaller that we can see. We're going to try and look for the nucleus of an atom. For this, we're going to play a little bit of a game. And for this game, I'm going to ask for 4 volunteers to come help me on stage. 1, 2, 3, and 4. Come on up here, please. Okay, and it turns out we have 5 volunteers, but that's fine. The more the merrier. So, is there one of you that likes to write things down? Yes, you like to write things down. Excellent. What's your name? David. Excellent. That's my second name. So I introduce myself as Michael, but it's actually Michael David. I just don't often use the name David, but that's a great name to have. So nice to meet you, David. What you're going to do, I'm going to move this here, and you're going to keep track of the score for this game. Does that make sense? Perfect. And I'll give you more information once you need it, but when you go to write, you'll write things here, okay? Excellent, thank you. And for this game, we're going to use this beautiful model of an atom and these model alpha particles. Can I get one of you to hold this frame here? Perfect, thank you. Oh, that's okay. Okay, so to explain what we're going to do, a little bit of background information. So, we already talked a little bit about electrons. Electrons are the outermost part of an atom. The innermost part of the atom is called the nucleus, and it's got a positive charge. And it was discovered over a century ago by a famous experiment, which is usually called the Rutherford gold foil experiment. And what Rutherford and his team did, they bombarded a thin sheet of gold foil, like aluminum foil, but a little bit more expensive. They bombarded it with alpha particles, which are the nuclei of helium atoms. And they had all these alpha particles hitting the gold foil, and to their surprise, most of them went through, some bounced backwards, and some were deflected. And from the number that were deflected, they were able to calculate the size of the nucleus. So here we have a model nucleus, which would be within a model piece of gold foil. And these volunteers here, they're going to help bombard the target with alpha nuclei. So I'm going to ask one at a time. Can one of you come over here? And I'm going to give you 10 alpha particles, 10 model alpha particles. So here's 7, 8, 9, 10. And then you're going to stand all the way back here. And you're going to throw them at the target. And we're going to count whether you miss or whether you hit. Is that clear? But stand all the way back here. Otherwise, it's too easy. And we're going to move the target just a little bit further back. Okay. And now we get to David. David, your role is, after he throws, count how many were thrown. So he's going to throw 10, and how many hit the target. Does that make sense? Okay. When you're ready, start throwing. So So that's one hit. Two. Three. Four. Okay, so 4 out of 10. Now we're going to do the same thing with our next volunteer. So here is 10. Let's have a go. One. And that was 3 hits out of 10, right? Okay, so we should see, total throws we have 20 throws now, like, because there were 10 and 10 that are thrown. So we should have, let's do like a running total. So let's do 20 throws, and we had 3 and 4, so 7 hits. Does that make sense? Okay, so now we have some preliminary results. We don't have enough results for huge statistical significance, but these results would say we have 7 out of 20 hit the target. They're good? Okay. So 7 out of 20 hit the target. That would mean that we would think our nucleus takes up about 7/20ths of the size of the frame. Does that seem reasonable? Is this about 7/20ths or about 1/3 the size of the whole thing? No, it's much smaller than that, right? So we must be doing something which biases it hitting the middle. Can anyone think of why we'd be hitting the target more often than we'd expect? Because we're aiming, so there's an intent and an aim. So if we were using alpha particles, there would be no aim. So now we're going to go a little bit quicker with our results. And I'm going to ask you, rather than aiming specifically at it, just take your handful of alpha particles and throw them all at it. Does that make sense? Like the whole handful. No, like the whole thing at a time. So whole handful just, okay? Okay. And there it looked like 2 hits and 8 misses, right? So we're getting a little bit closer to what we're expecting. Now we're going to improve this a little bit more by using a smaller target. If this was to scale for a real gold atom and a real nucleus for this 1 meter frame, then I'd be having one that would have a diameter of only 2 millimeters. There's no way we could hit that, so we're going to reduce it not to 2 millimeters, but we'll get down to 13 centimeters diameter. So switching for a smaller model nucleus. Okay, and now to make things go quicker and with no intent or aim, I'm going to get, can you come hold the frame? And can you grab 20 alpha particles and just 20 in one go throw at the frame? Can it look like 1 out of 20 hit, right? 2? Okay, so we have 2 out of 20. So with the new one, and let's draw like a new line, so this will be big and small, 2 out of 20. So 20 and 2. Okay, and from there, we should be calculating that this would be about 1/10 the size of the frame. Still a little big, so we're going to get an even smaller nucleus. And as I get the smaller nucleus, can each of you grab 20 of our alpha particles? And just before you throw, take a couple steps further back so there's even less intent and aim. And now, you'll need to help pay attention with me to see how many bounce back, how many go through, okay? Okay, go. That looked like one hit. Zero hits. Okay, so now we have 1 out of 40. So 1 and 40. So now that's 1/40 of the area. And if we think of the whole area, this is a 1 meter square. So we have 100 centimeters by 100 centimeters. 10,000 centimeters. If we have 1/40 of 10,000 centimeters, so like we divide that out, then it should give us an area of 250 centimeters squared. And if we do the calculations for this one, which I calculated on the back beforehand, we should be expecting a little bit smaller than that. It's only about 100, and we got 250, so we're not quite there yet. But we managed to get a reasonable estimate, right order of magnitude, for the size of our nucleus. So that was modeling the Rutherford experiment. Let's thank all the volunteers, and you guys can go sit back down. So that was one way we can model part of how we find the nucleus. Now we're going to see how we can use some of these techniques to discover some things we can't see with the naked eye. Remember, the theme throughout this is seeing the invisible. But before we do that, I want to get one more volunteer, a volunteer who likes to draw pictures. And this won't be for this experiment, but it'll be to give you a minute to draw a picture I'll use in the next experiment. So someone who really likes to draw, who wants to draw something big that everyone will see. Okay, and I see a hand high in the air back there, so you can come up and be my artist. And I see some hands still in the air, so I guess I'll call another volunteer for the next experiment. How about you? You can come on up here. Welcome on stage. What's your name? Ayman? Nice to meet you, Ayman. I'm Michael. So what I'm going to ask you to do, I'm going to give you these fluorescent highlighters, if I can open the box. Okay. These fluorescent highlighters, and I'm going to ask you to be hidden so no one can see what you're drawing, but come over here. Come over here. And I'm going to ask you to draw a picture just with this color at first. So draw a picture, anything you like, and let me know when you're done, okay? Well, that beautiful volunteer is drawing a picture backstage. Now we have a new volunteer. What's your name? Damila. Nice to meet you, Damila. I'm Michael. So here, I have a bunch of pens. Can you help me tell which pen is which? They all look about the same, right? So you're going to help me be a particle detective and figure out which pen is which. Can you handle that task? Don't worry, we have some tools to help us. So these pens, and we'll do it over here so they can see on camera. So these pens, come on over here. These pens, we'll hold them up for the camera. So these pens are all from the International Particle Physics Outreach Group. And they look the same, right? Do these look the same to you? They're about the same, right? Now here I have a magnet, and you can help me find one of the pens should be magnetic. Can you try and figure out which one is magnetic? So try touching on the different pens. Ah, so that pen is magnetic. So we managed to detect the presence of iron in this pen. And if we open it up, we'll see this pen is actually filled with iron wool, so it's magnetic. So with my assistant particle detector, we managed to detect a magnetic pen. So we have a magnetic pen there. Now we have a couple pens that are left. I've got a fancy tool over here. Stay here. This is a special kind of flashlight called a UV light, and it makes things shine in ultraviolet. Can you try shining it on the pens and see if you can help me find which pen might be fluorescent or phosphorescent? Do you see one that shows different than the others? This one, right? Look at it. We see that shining brightly. So this one has been painted with a fluorescent ink. So this one glows when we shine the UV light on it, right? Whereas the others don't. And we can see the difference there. So we found another one of the pens that we've separated. So this one was magnetic. We'll put it next to the magnet. This one was phosphorescent. Now we have two left. How do you think we can find the difference between the two? Do you have a good sense of smell? Can you see? Do the two pens smell the same? Can you try sniffing them? Parazo? I don't know what that means. Different. Oh, they smell different. Does this one remind you of anything? Maybe you're too young to know this smell. No? This one smells like coffee, and coffee is a strong smell, and we can detect that with our own bodies because molecules of the coffee can go into our nose, and we're able to detect that. So now it looks like you're getting a little bit bored, so maybe I'll do the last one on my own. Do you want to help with the last one? Yeah? Okay. So with this one, it's going to contain something that's radioactive. And I have this special device. It's called a Geiger counter. And what it does is it detects radiation. So we're going to move it around, and if it detects a high level of radiation, it'll start beeping. Don't worry, it won't be a high enough one to hurt you at all. The radioactive material here is potassium chloride, which is edible. People eat it. But can you try testing it next to the pens? Oh, already when I got it this close to the pen, do you hear it beeping? Yeah, I think you can hear it beeping, right? That meant that this pen was radioactive because of the potassium iodide. So now we've sorted out our 4 different pens and what the mystery substance was. So you're a junior particle hunter. Way to go. Thank you for your help. Let's give her a round of applause. And now you can go sit back down. Meanwhile, let's see how our artist is doing over there. Do you need much more time? Oh, that's beautiful. Okay. I think we're just about ready to show it to the audience. What do you think? Okay, so to unveil it, I'm going to ask if we can turn the lights down again, and if we can turn the screen off so we get things nice and dark, and we're going to unveil it under some colored lights. So here, I've got a powerful red light, and we're going to look at this beautiful artwork that's been made. So let's have a look at, let's have a look at what you've created here. Beautiful. Let's give that a round of applause. But I don't see much. Do you guys see much there? No, so what were you doing the whole time? Where did your drawing go? Ah. Okay, so this shows us the principle of fluorescence. And that tells us about how electrons are interacting with photons. So we saw a little bit about what electrons do with the flame test. We saw how we can tell where the nucleus is. Photons can interact with electrons, and we see that the photons of blue light have the most energy. They're making the yellow fluoresce, and the red has the least energy. They don't fluoresce. So just like the flame test showed us what the electrons were doing, this shows us how electrons are interacting with photons. And we can see different colors of light. Blue has the most, followed by yellow. And then red has the least, and that can't make it fluoresce at all. So that's an example of fluorescence. Now let's give our artist a round of applause, and you can go sit back down. And we can turn on, or no, don't turn on the lights yet. Sorry, I asked for that too quick. Leave the lights off. I forgot the next part of this. Okay, so we can look at different examples of fluorescence, and you can see with the blue colored light we can get these markers fluorescing, but we get it even better with my UV light that we use to detect the unknown pen. Now, inside of a particle detector, and we're getting near the end of the show, so we need to link all of this to how an actual particle detector works. Inside of a particle detector, there's something called a scintillator. And a scintillator isn't much different than a phosphor. So if I have the light shining on this bottle, and this is just tonic water like you can get from the grocery store and drink, it will fluoresce, or it will scintillate, so it's detecting when we have photons going through it, it'll get a photon of a lower energy. In the top, I have olive oil, and I'll show you olive oil just like you could use for cooking or for eating on salads as well. And olive oil contains chlorophyll, and chlorophyll has the interesting property that it will fluoresce red. And so we see that reddish-orange color there when we have the UV light on it. So we have two examples of different fluorescence. Now, inside of a particle detector, when we have a high-energy particle going through a scintillator, we'll have it flashing light only where it's been excited by the particle going through the detector. So we have these two examples of different colors of fluorescence, which can model different types of scintillation in a detector. We can also see curious things like these beautiful red cucumbers. While I'm showing these, can we turn the lights back on in the room? Can we turn the lights on? Perfect. And you see, these aren't actually red cucumbers. They're regular cucumbers that were fluorescing. To prove that, because I need a bit of a snack after some time on stage. This is indeed just a regular cucumber. Okay, so now we've gone over Okay, now we've gone over a bunch of different principles that happen for detecting the invisible. Now is the time to invite you to become part of a model particle detector. So, I mentioned we have the idea of scintillation. And scintillation, if we have a particle going through something that can fluoresce, we'll get light being emitted. But no, I don't need a volunteer for this part. I need everyone to be my volunteer. So, everyone's going to be a volunteer. No, everyone's going to be a volunteer for this part. So, with my UV light, that's emitting an uncountably large number of photons. It's emitting billions of billions of billions. Inside of a particle detector, we want to detect a single photon. So instead of shining bright, it'll just get one photon of light. That can make an electron excited, but that's only one electron, and we can't detect that. We need at least hundreds of electrons to do so. So they use something called a photomultiplier. What happens is a single photon can excite an electron, but then that electron can excite two more electrons. Those two can each excite two more, so we have 4 electrons excited. Those 4 can each excite 2 more, so we have 8 and then 16 and so on, until we get to about 100, which we can detect. So you guys are going to help me detect that. How are you going to do that? I want everyone in the room to think of a number between 1 and 50. So any number you want between 1 and 50, like 1, 2, 3, 4. And we can tell where particles have gone through in a detector. So as you can see, some of this gets a little bit complicated, but we started off pretty simple, just seeing how we can detect molecules of air, then electrons, then atoms, then photons, and how we can put that all together in a detector. So that concludes this voyage as particle detectors. Thank you for joining me in the journey.